Hello everybody and welcome to week 4. Alright, so normally at this point in a 372 semester we're going to start talking about the exam that should be coming up next week, week 5. It's coming up quickly. So I will be sending out a review at some point this week so that you can all see it. I'll try to have it loaded by Wednesday, which is the day that you were supposed to have told me which testing site you're going to be attending. But first we have to finish up sequences. We're going to kind of expand what we've been doing, talking about sequences and how to get a formula out of those things. And then we're going to go ahead and talk about series as well. So that'll be on the next class period is series. So here we go. In D2L, I'm going to load up something called stretching sequences. This is what I would normally do with you in class, talk to you about something to this effect. And you can see there's actually like a template for it, so you'll see something that looks like this. But basically what's going to happen is I'm going to build some figures, some pictures. I'm going to use color tiles to do them. And we're going to work off the figure number. Now this is going to be important for us because this is like the first figure, the second figure, the third figure, the fourth figure. And if you watched the videos last week, then you should have heard it said something like the first term, the second term, the third term, the fourth term, until we come down here and we're like, hey, can we generalize that thing? How about the 10th term, the 100th term, the nth term? So the nth term, remember, is my general pattern. So it's my generic formula, and that's where we're trying to get to on all of these, right? So I'm going to just throw some color tiles up here. I'm going to reproduce these 3 pictures, and we're going to talk about what comes next, and then what do we think is going on. So the first one is just 2 color tiles side by side. The second one is still 2 color tiles side by side, and color is not going to matter here at all. And then it's 2 color tiles underneath it. Okay, and then the third one, I'll put it over here, is 2 and 2 and 2. And again, if you don't have color tiles at home, you could use other things to make this happen. But you're going to look at that and you're going to go, okay, what do I think is happening? And in the problem it said, I want to know the perimeter. So first off, what do we think is happening with, let's just start out with the entire tiles here. 2, and then the next one's 4, and then the next one's 6. And then we think there's going to be 8 in the next picture, and then 10 in the next picture. So there's 2 different activities that come out of this. One is figure out the area, and the other is figure out the perimeter. So I actually want to start out with the perimeter, or I'm sorry, with the area first, so we can just see how that looks. And then we'll talk perimeter later if we have time. Okay, so area, what I'm talking about. Okay, if we had the figure number here, okay, which is in that table, the first term, the second term, the third term, and then the area would be in the number of tiles, right? Okay, so if I call this 1 square unit, then this area for the first picture would be 2, right? And if I talked about this area right here for the second picture, there would be 4 tiles there, right? And the next area would be 6. And then, like I just said a minute ago, you know how many are going to come into the 4th picture. That would be 8. And the 5th picture would be 10. And I think it becomes pretty easy for us to see what's happening here as far as area. We're definitely adding by 2 each time, right? Last time we called those finite differences, or my rate of change. rate of change. And if you're in, say, the Math 361, 362 classes, maybe you've started seeing some rates of change in there. So those are my rates of change, and I know because the first difference there is a constant that this is a x to the first equation, which means it's linear, right? So just by kind of looking at my table, I can see that whenever I see what's going on. It has to be a change of 2 on what would be the dependent variable, or if you were thinking x's and y's, it would be the y value, right, if I were graphing this guy. So it has to be the change of 2, and then the change has to be +1 on each of these, right? If I had skipped 1, for instance, if for some reason I had the 7th picture here, it's okay for me to skip by 2 as long as what? On this side, I wouldn't skip by 4 anymore, or skip by 2 anymore, I'd skip by 4, right? So that would be a 14. So we could see, hey, that's +4. And the slope there would be 4 divided by 2, right? Because that's what we said we were looking at, was the slope, 2 divided by 1. If you remember from your rise over run kind of stuff, I think we've talked about that before, that the rise would be my y values, the run would be my x values. So whenever I look at those, I'm looking at the difference or the ratio between the rise over the run. So it's okay to skip here as long as I skip, proportionately speaking, the same over here, okay? So 2, 4, 6, 8, we see what's going on there. And we said last time that it's really easy. We see that this is a linear function for me to come back and say, hey, what's that formula? Y equals mx plus b, right? And so on this one, again, I need a constant rate of change. It's really important that it's a constant. And I have that here. So we said that my constant rate of change here is a 2. So it's 2x, and I just need my plus b. So whenever I look at that, I say, oh, what's the y-intercept? Again, I don't see it. So I'm going to back up to the 0 term, because that's where I find my y-intercept, is at x equals 0. So if I back up there, then that's a 0 also. So it's y equals 2x plus 0, and we all know, hey, if we got a plus 0, we don't really need that. So this is just y equals 2x, which you probably could have guessed because you were really smart and you said, hey, Dr. Webster, stop right there. We're doing 2 times 2 gives me the 4. 3 times 2 gives me the 6. 4 times 2 gives me the 8. So there's always this additive property that's going on here that lets me know for sure I'm dealing with a linear function, right? But there's also a multiplicative process, because we should know by now, I hope, that multiplication is just repeated addition, right? So we could have come across this way. 1 times 2 gives me 2. 2 times 2 gives me 4. 3 times 2 gives me 6. And whenever I can do that and I can see, hey, look inside of there, I know that's just multiplicative. I can say, hey, hang on a second. I see what I'm going to end up with as my slope, so I can just go ahead and stick that in there whenever I know it's a times 2. The nice part about this, I mentioned whether something was proportional or not, and you may know from some definition in the back of your brain that these functions are always proportional whenever, if you think in algebraic terms, the y-intercept is 0, 0. So if the y-intercept is 0, 0, then you truly have a proportional relationship. And you're going to see some of that proportionality relationship. You're going to see mention of that proportionality come out in some of the middle school TEKS, you'll see them in there. They actually do talk about, honest to goodness, teaching students in middle school the difference between, hey, this guy's proportional, and wait a minute, that guy's linear. Now, the interesting thing is that all proportional guys like this are actually going to be linear equations, right? This is still a linear equation. However, it's a really special guy because he doesn't have a y-intercept, basically, or you could think the y-intercept is 0, right? So he's proportional because I can just say, oh, all of my term numbers are being multiplied by some number there that is the slope or the ratio that I'm multiplying by, okay? So interesting stuff coming in there if you're looking at the TEKS in middle school. All right. The next thing that they want to do with this is they want to say, hey, same exact picture, so I don't want to put the color tiles up here again if I don't have to, but talk to me about the perimeter. Oh, by the way, this is my general pattern, right? And in your activity, it might say, give me the nth guy instead of the x guy, so he would be 2n. Y equals 2n. No worries. Okay, I might have to put the picture back up here. So the next one, the one that's actually on the sheet I'm going to put back up here, says, talk to me about perimeter instead. Okay, so area, that one's kind of nice and easy because it's a rectangle, and we all know length times width, so we probably could have come up with that pretty fast anyway, because we could have said, hey, look, all of these guys have a width of 2, and this one's a length of 1, and a length of 2, and a length of 3, so it's seriously going to be a 2 by 3, right? A 2 by 2. So we probably could have even cheated more on that last one and just said, hey, I know the area of a rectangle is length times width, so I can come up with 2x really quickly because it's a constant width here. That's where the 2 comes from. And then these are just increasing by first figure number, 1 row deep, 2 rows deep, 3 rows deep. If I were to draw the next picture, it would be what? Yeah, 4 rows deep. So it'll be 2 across and 4 down. So if you draw the next picture, which it wants me to do in here, 2 across and 4 down. You can do that until you get to the 100th guy, or the 10th guy might even be hard. So you can, on your thing, whenever you're doing it, you can write like 2 by 10, 2 by 100, 2 by n. So you can see what's going on there. But this one actually wants me to come up with perimeter. So let's talk about perimeter for a second. And they helped me out a little bit. They said, hey, I'm going to throw these up here. On the picture that's just 2 by 1, so it's 2 across and 1 down, that was my figure number 1. The perimeter, now I'm not talking about area, right? Now remember, perimeter means the outside edges, right? So how many outside edges do I have? 1, 2, 3, 4, 5, 6, right? So they gave me that in the problem. And then they said, hey, figure number 2, I'm just going to add on here. Sorry, I'm kind of limited on my space right now. That's a 2 by 2. And if I look at that, it's 2 plus 2 plus 2 plus 2. That's 8. And the next one is the 2 by 3. And it's 2 plus 3 plus 2 plus 3. And some of you guys probably know a bit of the perimeter formula, which would probably help me out here. But if you don't, then you're seeing 3 plus 3 is 6, plus 2 is 8, plus 2 is 10. And again, I'm seeing a lovely constant ratio in there, right? Constant finite difference in there. So I think, oh my gosh, this is working out great. So they want me to draw the fourth picture. Again, we know that would be a 2 by, let me see if I can scoot it a little bit here. 2 by 4, 2 by 4, sorry. I have to get my chuckles where I can. So that would be a 4 plus a 4 plus a 2 plus a 2. A lot of you know that the actual formula for perimeter is 2 times the length plus 2 times the width. So you already kind of know what's going on there. Unfortunately, that requires me to have 2 different variables. But we know that our width here is what? Staying constant at 2, so you could substitute in there, and I'm thinking you'll get 2L plus 4, right? If you know that your width is 2L plus 4, because we know our width is 2 on all of these guys. So hold that in the back of our minds, because we kind of know that formula, and that's helpful to know. But I want to develop this like you would actually develop it with a child, like in the middle school levels, because some of them aren't always going to be as nice as that for the perimeter formula. So I want to make sure we can do it using our table, using which term we're on or which figure I'm on. So the fourth guy here, I don't think I said, was 4 plus 4 is 8, plus 2 is 10, plus 2 is 12, right? Okay, so we've got, again, a nice little table going over here. And I see the differences in here. Plus 2, plus 2, plus 2. And I see that it is going up by 1s on this side. So I feel like I'm doing pretty good. I know I've got a nice, pretty constant rate of change here. So again, this is going to be linear, right? And whenever I think about that, I'm like, okay, so let's go back to our linear equation. We know that guy. He's y equals mx plus b. But we know that our m is a 2, so sorry, I went ahead and substituted m in. So 2x plus b, but I just don't know what my b guy is. And now if I go backwards, I'll see, hey, work your way back to get the y-intercept. That's a 4. Hey, that's what we said. Okay, so just using my nice pretty table over there, I can get to the result we knew we were probably going to end up with, right? So I can see, hey, that is my y-intercept. This would be like the case of what if I didn't have any rows, and what they're saying is, well, we would basically be one-dimensional because we're 2 across, so we'd have the 2 on the top and the 2 on the bottom, but not any rows. So it's kind of like my physical representation kind of dies there because I can't turn back and have 0 tiles and show that, and which is sometimes why people are like, hey, I can show 0, 0 because that's no tiles, no figure. No figure means no tiles, but it's kind of hard to show no tiles or no figure number, no perimeter, or for perimeter. This would be similar to the one we did last week with the cow, where if we take out all the cows out of the middle, we still have the 6 bales of hay, right? So we still have some kind of a constant added on at the back. Okay, so that's kind of the idea of what we're looking at here. Of course, that was kind of the easy one, so we got to make it a little bit harder. Oh, by the way, do I see a nice pretty multiplication coming in here in the middle like I did in the last one? Maybe not, because if I multiplied here, it would be 1 times 6 gets me 6. But if I went 2 times 6 to keep it the same number I'm multiplying by, clearly that's not 8, right? So sometimes, and I'm just going to tell you, sometimes part of the process of doing these things, finding the general pattern and things like that, is actually like trying stuff and seeing that it doesn't happen. So I don't see a 1 times 6, and I don't see a 2 times, in fact, this would have to be 1 times 6, this would have to be 2 times 4, and then this 3 times what gives me 10? It would be like, what, 3 1/2? 3 1/3, 3 1/3, right? So there's not any one thing I can multiply by here. But if we go through with the normal formula that we found over here, the general, 2x plus 4, and say, hey, does that work? 2 times 1 is 2 plus 4. Yeah, that gives me 6. 2x plus 4, 2 times 2 is 4 plus 4. Yeah, that gives me 8. So it's not a nice pretty multiplication going in on there, but 3 times 2 is 6 plus 4 is 10. Once I know my general pattern, I can see, oh, that is a closed formula. 2 times 4 gives me 8 plus 4 is 12. So it will work for me, right? So in this thing, for instance, they're going to say, Skip, tell me what the 10th guy is, and you don't have to go and build 10 of these pictures, right? You know, it's 2 times 10 is 20, plus 4 is 24. Done, right? You don't have to go do that for the 100th guy. You know, 2 times 100 is 200, plus 4, 204. Okay, so you can kind of use some of those deductive type powers that we have to figure these things out. Okay, Next one I want to show you on this same kind of thing with the stretching sequences. The pattern's a little bit more difficult, so instead of starting with the 2 by 1 guy, they actually start by 2 by 2 guy. So let's think about that. So the first one actually has 4 tiles. The next one has 6 tiles. And the next one has 8 tiles. Okay. And again, we could do the area, but they're actually in the one that you're doing, they're just asking me to jump straight to kind of perimeter. So let's look at it. 2 plus 2 plus 2 plus 2, well that's 8, but wait a minute, we had that before, right? We had one that had a perimeter of 8. It's just that in the last example, that was my second picture, right? Right here. This was my second picture. And then, wait a minute, that guy right there, we already did him, right? 2 by 3. He was here, but he was my third picture in the last one. So wait a minute, we know that there's some kind of weird pattern going on in here. We can see it. It's just like they dumped out the first guy. We just don't have the figure number 1 that had 6 as the perimeter. So let's take a look at that and what that would look like for this particular pattern. So this is a different problem. And again, remember that we're starting with the 4. And of course, at some point we can draw pictures instead of using the actual model. And then we're going to the 6. And then we're going to the 8. And again, I'm thinking to myself when I draw these, look, they're all too wide. They're not changing in their width at all, so that's kind of nice for me. So figure number, or term number, if you'd rather use term number, that's fine. And then the perimeter. And this one, 2, 4, 6, 8, right? So the perimeter is 8 on the first one. The perimeter on the second guy, yep, that's the, what, 4 plus 4, I'm sorry, I skipped. 3 plus 3 is 6, plus 2 plus 2, that's the 10. And then next is 4 plus 4 plus 4 on the third guy is a 12. And what we're seeing is, again, we're going to get exactly what we had here, 8, 10, 12. The next guy would be 14, right? 8, 10, 12, 14. Does everybody agree? Because I'm adding 2 each time. And on the other side, I'm adding 1 each time. So they're both constant. So when I figure out this ratio, 2 to 1, that means that my constant rate of change is still a 2, right? So that's my slope still. So nothing's changing there. That's interesting. But they started me at a later figure, so to speak. If I work backwards, what's that going to be for the y-intercept? A 0 and a 6, right? Okay. So real quickly, we can get that formula, y equals 2x plus 6. But something else is going on in here too, so we're going to look at that for just a second. Y equals 2x plus 6. Okay, that works for me. I can see it. I can put in, for instance, right here, 2x plus 6 and say, okay, let's think about it. 3 times 2 is 6 plus 6, that's 12. 4 times 2 is 8 plus 6, that's 14. So it's definitely working. I have a good general pattern, no worries about that. But somewhere in my brain I'm going, gosh, you know, if I didn't happen to know that that was a linear equation, I might be in trouble. Okay, so I'd like to play with that just a tiny bit and see what's going on. When I look at my pictures here, I see, again, the widths are all 2s. Everybody agree? Sometimes it's going to pay off for me to kind of look inside and see what are the dimensions that are going on. So the dimensions that are going on here, it's a 2, and on the side it's a 2. Here it's a 2, this is a 3, here it's a 2, that's a 4. Now that was interesting earlier to me because earlier, whenever I had that original figure, I even mentioned, right? It's 2 across on each of them, but 1 row deep, 2 rows deep, 3 rows deep, right? So 2 across, and these are all the numbers of rows. But now that they've kind of messed me up and changed which picture I'm on, it's like, no, that's not what's happening anymore. This isn't the 1 row deep for the first term. This is my first term, and before this was a 1, right? But that's not what I've got. I've got a 2. And this isn't my second term anymore. Instead, it's a 3. And this isn't my 3 rows deep. Instead, it's a 4, right? So what are they doing to each of these things that's going on? If the figure number was here, it was a 1, they're not just doing 1 anymore, right? They're doing what? Yep, 1 plus 1 gives me the 2, right? Compare it back. This isn't the 2, this is the 2 plus 1, right? This isn't the third guy, this is the third guy plus 1. So if you think this is the picture that goes with the first term, so here's what I had earlier. First 1 row, 2 rows, 3 rows. This is the figure that comes with the first term. This is the figure that comes with the second term. This is the figure that comes with the third term. But instead of it being 1 row deep, like it was the last time, there's an additional plus 1, right? Instead of it being 2 rows deep, so last time it was just that deep, now it's 3 rows deep, so it's 2 plus 1. And instead of this being 3 rows deep, now it's 4 rows deep, so that's 3, third figure, plus 1. So I'm kind of looking at that and going, can I do something weird with the dimensions in there, right? So if I could just do something kind of interesting with the dimensions, that might pay off for me. So I want you to kind of look at that and think about it. Is there a way that I can express this using what we already have? Well, that's the unknown. That's the figure number, right? First term, second term, third term. So can I list that as an X? And then can I do something with this guy? Plus 1, right? Okay. So now whenever I'm looking at that, I'm like, okay, well, if it was area, it would be kind of nice because I just go 2 times, because the length times width thing, right? 2 times x plus 1. That would be really easy for me. Unfortunately, this one's not area. We're doing perimeter. So it makes life a little more complicated. But we know the perimeter formula, or if you're not really sure, you could just say, hey, I'm just going to add all the way around, whichever way you feel more comfortable with it. But I'm going to use 2 times length and 2 times width. So 2 times, I'll come back to length, plus 2 times width. And we already said we know that the width on these guys is a 2, right? Okay. So I got this out here. That's the 4. I actually had that a long time ago when I did 2 or 3 examples ago, right? But what the heck am I putting in here is the question. Yeah, I'm going to put in x plus 1, right? Because that's how I'm getting how many rows deep it is. So that's x plus 1. So this is actually, whenever I work it out, 2x, because I'm going to distribute, 2x plus 2 plus 4. Oh, I'm getting goosebumps. That's a 2x plus 6, right? Totally cool math coming in right there. So I can kind of compare back to the figure number and say, hey, what the heck is happening in that figure number? And hopefully it will help me to see, oh, that if I don't know, if I can't work with it, then in this case I could have done 2 plus x plus 1 plus 2 plus x plus 1 and just added all those together, but instead I chose to use the perimeter formula and multiply it. It doesn't really matter. Any way you go, you're still getting, I've gotten now 3 or 4 different ways, 2x plus 6 there, right? Okay, so those are all kind of similar problems because why? Yeah, they all had a constant width, right? So you know we can't just leave it that nice for you. Just couldn't do it. So before we do anything else and moving on, we got to look at a figure that's not quite so nice. So in your stretching sequences example, it's number 4 in the thing, and I'll show you their picture. The first one is 2 across, 1 down. The second one is 3 across, 2 down. The next one is 4 across, 3 down. So you can see what's happening in there. I'll draw a picture here so that I can play with it. So it's a 2, I'm going to write it here, 2 by 1. This one is a 3 by 2. Let me make sure I'm drawing this right. Yep. The next one is a 4 by 3. And your pictures don't have to be perfect or anything like that. Okay, and I'd like for you to take a second right now and actually draw the next one before I do it. And tell me what you think is about to happen. Okay. Hopefully you're drawing something that looks something like this. And it's got what across? 5 across, 4 down. Okay. Before I go any further, though, I want to talk about my figure numbers because I know sometimes this bugs people. So if I was in a sequence, this would be my first term, this would be my second term, my third term, and this would be my fourth term. By the way, this is a sequence, right? Because I've just got a sequence of different pictures going on in here. So it really is. And we're going to stick with, let's stick with perimeter. Let's do area first. I like area. Okay, so over here I'm going to do the figure number, or you could say term number if you prefer that. It doesn't matter to me. Whichever way you want to do this as your work is fine by me. And then over here we're going to say area, which is number of tiles. Okay, because area is normally pretty easy. Area is normally a little easier than perimeter. So let's start there. So for that, what are we doing? And I want to actually do the process here. So remembering that area is length times width. This guy is a 2 by 1. This guy is a 3 times 2. This guy is a 4 times 3. This guy is a 5 times 4. And I want to compare those as best I can to stuff we know. Well, really, the only thing that I know coming into this is which figure number I'm on, right? So I know I'm on figure number 1, 2, 3, or 4. And what I'd like to do is say, hey, do you see that particular sequence of numbers anywhere in either the dimensions of the pictures or in what I've got out here? And I say, yeah, I see it. Hey, hang on a second. Right here, first guy, second guy, third guy, fourth guy. If I did the next guy, I don't want to draw him, but if I did the next picture here, that would be a 6 by 5, right? And that would be the fifth guy, and then the sixth guy, and so on and so forth. So what the heck is that? Again, this is just my x, right? Or your n. Let's do n because we're trying to find the nth term here. Okay, so that's just my n. That's no big deal. And over here, we're going to compare that to the figure number. So I know somewhere in my formula here, I'm going to have an n going on. And somewhere over here, I'm going to have something related to the n. Hey, wait a minute. Didn't I have that a minute ago? Right here, we had the second guy, or we had 2 down, 3 down, 4 down, right? 2 down, 3 down, 4 down. And I said the 2, how does that relate to the first figure? Well, it's the first figure plus 1. 3, how does that relate to the second figure? Well, it's the second term plus 1. Third term plus 1. Let's see if we can do that. Is this 1 plus 1? Yeah. Is this 2 plus 1? Yep. Is this 3 plus 1? Yep. And so on and so forth, right? We can see it. We can see that what's happening over here on this side, on the length side, the depth side of these pictures, is that I'm taking the figure number and I'm adding 1. Well, what does that look like? It's n plus 1, right? We just figured that out a minute ago. So if that's x plus 1 or n plus 1, and what are we doing in between these? This and this. It was 6 times 5, 5 times 4. So in between these, there's going to be multiplication, right? Oh my gosh. Now hang on a minute. I didn't fill in these numbers here. The area here, sorry. The area here is 2, 6, 12 and 20, right? 2, 6, 12, and 20. Yeah. So hold on a second, because that's not linear anymore, right? And that's exactly what I want to think about whenever I'm looking over here. I've still got my constant rate of change over here on my independent variable. Those are still going plus 1, plus 1, plus 1, right? But something weird's happening over here. This is plus 4. This is plus 6. This is plus 8. Oh, it's the first one like those we've had. Man. So this is not a constant rate of change, right? Now, fortunately for us, we came up already with what the formula is, because we had a nice pretty model that we could use. And that's why sometimes modeling is nice, because I can see, hey, what's going on over there? And I can just use the model to come up with my equation, which is lovely. But I'd kind of not like to know what the heck is going on over here, so that I can see, hang on, what kind of equation is this? It's got an n times an n. That's going to be n squared, right? So let me just write up real quickly what my formula looks like. It's either y equals, I'm going to rearrange it a tiny bit, n times n plus 1, right? That's the same thing. Okay. Or if you were feeling creative with it, or feeling like you could do a little math, we could distribute that n through, right? So that would be n squared plus n, right? Are we okay with that? So what we're saying is we've got this nice pretty multiplicative property here, but I've turned it into a quadratic formula. So sometimes we can get quadratic formulas out of these. Let me go ahead and put the fifth guy out here. The fifth term plus 1 still was going to be what? 1, 2, 3, 4. Fifth term, 6 times 5 was 30. So what the heck's going on there? Plus 10, right? For my plus 1. Definitely not a constant ratio that I can multiply here. It's not a steady slope. It's not a constant rate of change. Nothing like that going on for me. So I got to figure out what the heck's going on. And how could I have told that that's going to be quadratic? Because this is kind of interesting. Quadratic. Yay. It's a little more complicated, right, than having a the whole linear thing going on here. So what you can do, okay, first of all, we got this model. It's lovely. It gives me a nice formula. I can figure it out. But if I'm just looking at the table over here, maybe some of you are screaming into the thing, look at the second differences. And if you were, then you would be absolutely correct. So let me look over here. If I'm looking at the first differences here, I start seeing a little bit of a pattern in it, right? That's why I went one more term so I could see it. 4, 6, 8, 10 is what I'm adding. So maybe you're thinking those are all evens. Plus 2, if I'm doing differences, plus 2, plus 2. So this would be called the second differences, or sometimes I'll call it the second layer. Okay, so I did one difference, and it wasn't a constant difference, so I know it's not linear, but it didn't give me anything to go with. So I'm like, can I do anything else? Hey, wait a minute, I kind of see a pattern inside of the differences, right? So to do some of these can be really difficult. You have to kind of sometimes look inside of what you're seeing inside of the pattern. So this is a pretty easy pattern, 4, 6, 8, 10. I see it's evens. So I can go plus 2, plus 2, plus 2. And look here, I have a constant second differences. Okay, constant second differences. Well, that's interesting, because if I have a constant second differences, then I have a quadratic formula. I know that this exponent here is a 2. Constant second differences. I wonder if that's by coincidence, and the answer is absolutely not. So if we had a cubic for instance, picture here, and I thought, hey, I've got a cubic formula coming out, then sure enough, if I did the pattern over here, the third constant, or the third finite differences would be constant. So third differences, the same constant, gives me a cubic, or x to the third power. Okay, so there's not my mistake. It's actually kind of a cool mathy thing that comes out here. And I'm going to give you a little bit more to go on that so that we can see it. I will say that sometimes, of course, the cubics and the exponentials can be difficult to deal with. So I'll actually show you a little bit of calculator work here in a minute that might make your life a little bit nicer. And of course, if I'm showing it on your calculator and you're allowed to use your calculators on the test, then you could certainly show me or give me your answer from the calculator, but at some point you'd have to show me some kind of work to go with it. You can't just say, hey, that's my calculator answer. That's not going to work. Okay, so you got to show me something that says, hey, I did all these differences and I realized the third differences were where it was constant, so I realized that was cubic. And so then I went to my calculator and did the quadratic or the cubic regression so that I could see that. So doing things like that might help you out a little bit. Real quickly, an interesting thing that's happening here to me is that I have n squared plus n, but I don't have the c number here, right? The c value in the quadratic. I don't have a constant. So let's look real fast. Go back again to my 0 guy. 0, what do you think this difference would have been? It was 10, 8, 6, 4. Yeah, this one should have been a plus 2, right? That would have kept me with my second differences being the same. And if it was a plus 2, then going back would have been a 0, right? Which means that my y-intercept here is 0, 0 if you were graphing these out on a nice pretty scatter plot or something. It would be 0, 0. And then whenever I see that, I'm going, oh, that means it's a plus 0, right? Similar to whenever we had the proportional a minute ago, but this is in the quadratic, so I just don't have a plus c formula. Real quickly, so everybody knows what the heck I'm talking about there. If you'll think back in the back of your brain, I think maybe you'll come up with the quadratic formula. And the general form of a quadratic formula is that y equals ax squared plus bx plus c. Okay. And what we know about this particular thing, by the way, was whenever I looked here, did I have like the slope, so to speak? The slope was the same as what the second difference here was? No, it wasn't, right? So the thing that worked for me in linear doesn't work for me here in quadratic, unfortunately, but I will show you a couple of little patterns that might help you as we go along here, because quadratic's not too bad. First thing is we know that this c value is always my f of 0, or the y-intercept, right? Even in a quadratic, it doesn't matter. Wherever that's crossing, what you're saying here is, if that is 0 and that is 0, then I will get the c. So that is my y-intercept, where all of the x's equal 0, right? So that is the interesting thing. And then the other kind of interesting thing that happens is we'll see our a value coming out, and it'll be 1/2 of the rate of change on the rate of change. Okay, 1/2 of the rate of change on the rate of change. And what that means is my second differences are constant. So let's think about that for a second. If this first level here is my rate of change, and that wasn't constant, then when I do this second level, that's the rate of change inside of the rate of change, right? So it's the rate of change on the rate of change. So if I'm looking at that, that's the second differences, or the second rates of change. And if those are constant, then I know that I'm going to take half of whatever that number is, and I'm going to stick it in front of my x squared. So whenever I do that, here we go. It was a 2, and I've got a 1 sitting out there. So we didn't have to know that to be able to do that, but it kind of is nice to see that pattern coming out. Okay, so you might see that as you go along. All right, so a couple of things to think about. If I give you a cubic, it will certainly be a fairly simple cubic. Again, they're more difficult to work with, but I'll show you how that works in a second in the calculator. And the general form for that, I'm going to be nice, and I'm not going to give you any of the stuff that goes in the middle. So we all know a cubic could be like ax cubed plus bx squared plus cx plus d, right? And I'm not going to do that. I'm going to give you some kind of ax cubed normally plus a c, and the c will be your constant, and that will be the f of 0 just like up here. And then it'll be up to you to play with that a value and see if you can come up with something, or to use your calculator, okay? And again, if I get one of these, the third differences are constant. And I'm not going to write it, but that would mean that the rate of change on the rate of change on the rate of change is a constant, right? Okay. And then the other kind of common one that you're going to see, and you might see this in your homework, is, okay, linear, quadratic, cubic, exponential. Sometimes we do exponential functions, right? So what the heck is an exponential function? Actually, we've already seen some exponential stuff whenever we did last week the geometric sequences. It looks a lot like that. And basically what it means is instead of my having constant differences, I'll have constant ratios. So this is what I mean by that. The rate of change is multiplied by a number. Okay, so that particular formula, we already have something like that. It's going to be y equals a times, where a is just some constant, b to the, and it's normally x plus h, plus a k, where we got a, h, and k are all constants. And b is my base. Okay, and that's the number being multiplied over and over again, right? Multiplied. Okay, so we kind of worked a little bit with that last week whenever we did a geometric function, geometric general pattern. We just didn't call it exponential, so we didn't see that that was what we were doing. But I would certainly be able to do some of that. So we're going to do a couple of examples. I won't draw them out too long, I promise. I know I'm already over 40 minutes on this video, but I do want you to see some of what you might do in the homework that's coming your way. And so I have just some tables going on here, and I'm going to show you a little bit of calculator work that might help us. So I realize I'm not going to be able to zoom and do my calculator at the same time. So my first example looks like this. I'm just going to go revert back to algebra because we're doing algebraic reasoning. We're all adults and we all know what that looks like, right? So I've got a 0, a 1, a 2, a 3, and a 4. And I've got a 1, a -2, a -1, a 4, and a 13. They won't always be exactly consecutive numbers, but so you should always check. But a lot of times they will be. And in fact, in this case, I'm actually giving you the 0 guy, which means you know your y-intercept, right? That guy right there is my y-intercept. So I like to look at it real quickly and just say, hey, what's going on? And here I see to get from 1 to -2, that's actually a -3, right? And to get from -2 to -1, that's actually a +1, right? And then to get from there to there, that's actually from -1 to 4 +5. if I'm doing this right. And then, let me double check my numbers and make sure. Yep, okay. From there to there is a plus 9, right? Okay. So, definitely not seeing it right now. I say, hey, that's not constant, so it's certainly not linear. And then I say, I don't even see a pattern, like this isn't 2, 4, 6, 8 or anything like that. But maybe let me just kind of investigate and see what's going on down here at the second differences level. To get from -3 to +1, I would have to what? 3 plus 3 gives me 0 plus 1, so plus 4. And then from 1 to 5 gives me, yep, I would have to plus 4. And then from 5 to 9, I would have to plus 4, right? Okay, so yeah, I see, oh, nice, okay, it does have a nice, pretty second difference in there, doesn't it? Even though it kind of went wonky on me at first, I say, hey, second differences are constant. So that tells me what? Yep, this guy is quadratic. Again, remembering that x squared matches with the second differences. So I know I got some kind of a quadratic. I know what that general formula looks like. Y equals ax squared plus bx plus c. I even know a little bit that I could plug in here. I know that this guy right here is my y-intercept, so I can put that in for c plus 1. I don't know a stinking thing about the bx, unfortunately, but I do know that, hey, y equals, we said this a was going to be half of this second difference, right? So the second difference was 4, so it's going to be 2x squared. So I can sit there and I can kind of play with it for a bit and try to figure out what's my b term. You might go through and do some stuff like, so there's some interesting things you can do. You could add in an extra, I don't have space to do it, but if I hadn't written right through here, you could add in an extra little column in there and say, hey, what would it be without the bx? What if it was 2x squared plus 1? Okay, if it was 2x squared plus 1 was my actual formula, and on the first one I put in a 0, I'd still have a 1, right? But on the one guy, I'd have 1 squared is 2, 1 times 2 is 2, plus 1 is a 3. So I'd have a 1, a 3. And so you can do a similar type thing going in there and comparing, well, this is what I would have had, but I'm kind of short-handed. 1, a 3, I'm not quite getting there. And you can compare those to see a pattern. So can you compare y values to y equals 2x squared plus 1, because that's what it would be if there wasn't a bx, right? And if they're the same, then there's not a bx. It's just nothing there. But if they're different numbers, which mine was, then I need to say, hey, how can I compare that? So you can do that. You can go through and play with it. And I know you would get a particular number, but instead of telling you that number, I'm going to let you play with that. And I'm going to make sure we all know how to use our calculator a little bit. So I think on your syllabus it says you need an 83 or an 84 to be able to do this course, and here's one of the reasons why. If you've had the 361, 362 class, maybe you've done some of this. If you haven't, I'll try to go kind of slow, but maybe pause the video and rewind and stuff like that. So whenever I want to look at one of these things and say, hey, I just don't have the time to mess with this and figure that out. Like if you gave me this much work and you had all of that, and then you said, I plugged this into my quadratic regression on the calculator to get my b value, I would give you credit for that on the test next week. Okay? But you got to give me some work first that tells me there's a reason why you know you needed to go quadratic. Because otherwise, as far as I know, you're just guessing. Hey, what regression is it? Let's plug it in the calculator and see. And that's not what you should be doing. I don't want to see that. Okay, I want to see that you've actually been doing some thinking about it, doing some working with it, and that you actually know, hey, I need a quadratic regression, and here's why. Okay, so I'm going to scoot this up a little bit. And I'll probably have to move it a little bit. What you're going to be playing with here on your calculator, let me zoom in a little bit, sorry. I knew I was going to have to do more zooming. Focus. There we go. Nice. Okay, on your TI 83 or 84, these are, to me, the most user-friendly-ish of all of them. But if you have a Casio or something, then hopefully you know how to use it. We're going to be working with the stat button and the list button, okay? And the list is just the second part of the stat. So I'm going to drop it a little so we can see the screen. So whenever I hit the stat button, you can see that 3 options come up. One is edit, one is calculate, and one is tests, okay? So whenever I go into these, I'll show you just a little bit. The edit, if I hit one of those, you actually see L1, L2, L3. Those are list 1, list 2, list 3. So I can fill these in with my X values and my Y values, and then I can have the calculator do stuff for me. So that's what the edit button means. I don't want second, I want stat. Okay, over here are the calculates, and there's a lot of stuff in there you can calculate, but in particular, you might be interested in linear regression, and we want the AX plus B format. There's another one in here, we don't want that one. The quadratic regression, the cubic regression, and if I keep going a little bit, yeah, you don't want that linear regression. LN regression, by the way, is logarithmic regression. If you're in the 361, 362, you might be doing those. We're not going to mess with any of those. We might want exponential regression, okay? But for this one, and then over here on the test, there's some stuff you can do in there, like if you were in a statistics class, z-tests and t-tests and stuff like that. So, but for this one, we know this is quadratic, so I want to do quadratic regression. Oh, I'm sorry. First, I want to insert my stuff. So I went to that link, but then I moved on. So I want to put something into my L1 and my L2, and so those things are, the first is going to be, just like you would normally if you were doing a table. I want to put in my 0, my 1, my 2, my 3, and my 4. I think they only had 4, yep. Okay, and then over here I want my Y values, so that was 1 and -2. Make sure you're using the negative on the bottom. The negative way down here on the bottom, not the minus sign. Okay, -2 and -1. And I'm just hitting enter in between to make it go down to the next line. A 4 and a 13. Okay, and I know that I'm done if these are matched, so to speak. Like if I had an extra Y value. Sorry. If I had an extra Y value for whatever reason and I wasn't paying close attention and then I tried to make my calculator do something with it, it's going to tell me an error which was mismatched. So I'm going to clear that 6 out because I'm sorry. Let me delete him. I don't want him. I just want the one that I had above it. So there we go. I've got my lists in. Now I'm going to go back to stat. So right there. Right? Just barely to the left of the arrows and down one. Stat and calculate, and I told you we want quadratic regression. This calculator has one of the newer software systems in it, operating systems in it. If in my old calculator, older 83s and 84s, it doesn't have this, so I'll tell you how to do it in just a second. But just for now, I'll use this one. So quadratic regression, it goes ahead and it preloads for me list 1 and list 2. If you put it somewhere else, then you'll have to change those. And you do those, you see how that A starts popping up? That's the alphabetical button, so you'd have to use your alphabetical buttons to do that. I don't need a frequency list, but I kind of want to store it somewhere. So I'm going to tell it where to store. It says store regular equation. And yeah, I want you to do that. And for us, there's this vars button right here, just underneath the arrows. I'm going to hit that. And you see if I come over here to the right, arrow over, I get Y variables and it's a function. I'm going to stick that into my Y1 so that I can see it. And there it is. It says Y1. And then I'm going to come down and I'm going to tell it to calculate. So I'll go down there so it's flashing on top of the calculate. And I tell it to calculate. And it tells me, hey, here's your quadratic regression. Here's the formula I used. Your A is a 2, your B is a -5, and your C is a 1. So let's come back here real quickly. I had the 2 and I had the 1, but I didn't have the B, right? It's a -5. So now I know B is a -5 right there. Okay, so it gives me that. If I wanted to see this all put together nice and pretty, then I can go to y equals, there's the actual formula. It gives you a plus and then the negative, you know, that could be minus, that's fine. Okay, I can now graph this guy that was in the y equals up here on the top left. Is where I got the formula. On the top right, I can graph that. And there it is. It is indeed a nice, pretty quadratic. And if I want to take it one step further, let me come back to y equals. I see up here that I don't have any of these plots on. I'm going to come up here to plot 1 and turn it on. I know it's on now because it's dark. Okay. The normal default for plot 1 is, if you look at second